All right, welcome everyone to another lecture on data analysis. Now today we're going to get into what we call an ANOVA. Now I want to make it clear to you guys that many of you all will never use some of this information, and I'm sorry to say that. But the thing is, the reason why we need to present some of this information to you is because I need to assume some of you guys are going to go on to grad school, or maybe even perhaps into research. And this is where this information is going to come into play. Now, for those of you who will never use this information in terms of actually running the test, it is important for you guys to know, like I said always, is evidence-based practices, right? You actually looking at the literature and trying to find out the so to speak scientific truths, or the objective truths behind scientific experiments, so you can implement that into practice. And that's where this information will kind of help you understand. So in some cases it's going to be more conceptual for some of you, but then others it might even be somewhat practical. I will state this though, I am leaving a lot of information out, mainly because there's a lot of complexities to ANOVA and also statistics, some of them which are beyond the scope of this particular class. So without further ado, let's get into some of this information. So before we get into everything, let's just kind of cover an example, right? So that way you can kind of understand what to look for in the scientific literature. And let's take this scientific experiment as an example. And this one's titled Effect of Resistance Training Volume on Strength and Muscle Thickness. And here's the abstract of the study, abstract being just a synopsis of what they did. So essentially, they had different volumes of high intensity that they want to test. And they want to test it on isometric torque, meaning, so to speak, strength, and also muscle thickness. The way they did this is they set up 3 groups. They did one group with just 1 set. They did another group with 3 sets. And lastly, they had a control group that did nothing at all. And what they tested them on, again, was maximal isometric knee extension or strength. And they also tested for muscle thickness. Now, how in the world would you ever go about comparing those results? Well, everything is laid out in the scientific literature, and they try to do it in a way to where you can actually replicate the results, if I was another researcher. Now, sometimes when you get to this portion of a research article, it might look like a lot of confusion. And right now you're seeing the statistical analysis, the author's statistical analysis. And they write, and let's just kind of read out to it. It says, an analysis of variance, meaning they performed an ANOVA, right, to determine the differences between the groups. But you also see stuff like here, a 3x2 repeated measures ANOVA, as well as a post hoc test. And we're going to actually discuss what those actually mean. So when you read into this, you'll have a better understanding as to what they're doing to show the differences between groups. And here's how you're typically, this is how they report it, but typically how you're supposed to report it is, I'll show you guys in a little bit. So let's just talk about what an ANOVA is, right? And I'll just read this to you guys. An ANOVA, analysis of variance, is a parametric technique, meaning it can test hypotheses, used to determine whether significant differences exist among means from 3 or more sets of sample data. So essentially what ANOVA can do, it's very similar to what we've covered in terms of a t-test. However, some of the stuff that I'm leaving out is that an ANOVA is actually what we consider a robust test. In statistics, you need to meet certain assumptions about data. If you don't meet those assumptions, your value or your probability values are not as concrete, right? You can't take them as literal. However, in an ANOVA though, it's more robust, and you're more likely to it can still detect changes within your data set even though you violate assumptions. So that's why we consider a robust test. Now, one thing I want to cover is where it kind of gets a little tricky. And let's just look back at one of our examples where it says 3 by 2 repeated measures of ANOVA. Now, just by looking at that, you might actually think that there might be 5 or 6 variables listed in the group. That's actually not the case. There are only 2 variables, right? I'm sorry, there are 3 variables, but they ran 2 different tests, and I'll explain that. When they say 3 by 2 repeated measures of ANOVA, what they mean here is you have 1 variable here and 1 variable here. But each one of those variables has levels. And I'll give you an example. The first variable here is actually group or condition. That's the first variable. And why it's labeled 3 is because you have low volume, high volume, or control group, meaning that our first variable is actually the group or the condition. Now the second one here, where it's labeled 2, is actually the time point. So they ran 1 ANOVA on muscle thickness, both pre and post. That's why it's 2. So it's actually, this is time. So just to reiterate, the first variable is low volume, high volume, control group, and that is actually 1 variable with 3 levels. And this is also 1 variable at 2 different time points. And that's exactly what that means. So when you start to see some of these things, you have a better understanding of how they ran the actual test. Now, other ways in the literature that you'll see ANOVAs listed is sometimes they'll listen to factor, variable, or way. And what that means is factor does equal a variable, but factor also equals way. For instance, sometimes you'll just see people, scientists or researchers, just simply call it a factorial ANOVA, meaning that there's 2 or more different variables. Or they call it a one-way ANOVA, meaning that there's only 1 variable, but that 1 variable can have many different levels. You can also call it a two-way ANOVA. A two-way having 2 variables, but those 2 variables can also have different levels. Or for instance, you can have a 3 by 1, 3 by 2, 3 by 3 by 3. This two-way ANOVA is the same thing as this 3 by 1 ANOVA. It's two-way, meaning there's 2 variables. In this case, there's 1 variable here with 3 levels, and then there's another variable with just 1 level. And I'm showing you this information so that you get to understand when you read scientific literature what all that means. Now this is where I'm going to lose some of you guys, but I'm going to actually calculate all this in steps so you get an understanding of what actually is entailed with an ANOVA. Unlike the t-test as well as the regression, ANOVA gives us what we call an F ratio, right? And whenever you see that F ratio, you know that, hey, they ran an ANOVA. Well, that F ratio can also give us a probability value. Now we're going to actually break down the formula as to what that means. So essentially, an F ratio is the mean square of the residual divided by the mean square of the error. Now to get these 2 values, we need the sums of squares of the residual divided by the degrees of freedom to get mean square residual. We also need the sums of square of the error divided by the degrees of freedom for that particular group to get the mean square error. And we're going to actually calculate all that stuff. I will not test you guys on this particular information, but it does give it is helpful to see how this all works so you understand what this value is giving you. So whenever you see the typical way how you report your results in ANOVA is as such. And I'll read it out to you guys. An analysis of variance showed that the effect of volume on muscle thickness was significant. You have an F ratio. Here you have your degrees of freedom between the two groups, and I'll talk briefly about that. This is your actual F ratio, and this F ratio is associated with a probability value. So we have a probability saying, hey, volume did have an effect on muscle thickness. And I'm going to talk about the nuances behind all that. So just kind of recall this formula, and we're going to break it down. Now let's say, for instance, we are all scientists. Maybe some of you guys might be in the future. And I want to determine if any one of these groups at the top has any different effect on overall strength. So what I do is I set up an experiment, and I have some individuals train machines, some train barbell, some train dumbbell, some train kettlebell, and then also I have a control group that does nothing. And I want to track I'm gonna track the changes in overall strength. Now the null hypothesis for this one is that there is no difference between the group, and visually we can describe that as group 1 being machines is going to equal group 2, they're going to equal group 3, group 4, group 5. That is my null hypothesis. Remember, the alternative would be that there is a difference, meaning that somewhere along the lines one of these groups is different, or many of these groups are different from each other. But let's actually figure how we're going to figure all this out. So here are just some fictitious data that I made up of the differences in strength gains between all the different conditions. And let's just consider all these in kilograms, right? So each group in the machines, it just changes in kilograms. The first thing that we want to do to actually understand this is we want to sum the differences for each group, right? And I've done that here at the bottom. So we have 37, 55, 35, 44, and 31. Based off those numbers, you can already tell that, hey, there's a difference, okay? Now, is that difference actually statistical? Or is there a statistical difference? Meaning, is there a 95% chance that that occurrence didn't happen off chance alone? Meaning there was a reason behind why that difference occurred. The next thing we want to do is we want to get the mean of each group. So the mean change for each group is 5.29, 7.86, 5, 6.29, and 4.43. So as you're seeing there, it's the same thing. We see a difference between the groups. Again, we don't know if it's statistically different. Now again, we need to do some further calculations to get our F ratio. So we need to actually get the grand sum of each difference, and that is right here. Basically, it's the sum of all these values right here, and then add it across, and we get 202. But we also need to get what we call a grand mean, and that mean is the mean of all the means of the groups, and it's 5.77. So here we want to get our denominator, right? And that's sums of squares of the error. Now I don't want to confuse you guys, but the sums of squares of the error is also synonymous with within group differences. Sometimes you'll see that in the literature as within group differences. And I'll show you exactly what that means. So we want to get the sums of the squares of the error, or within group differences. So how we do that is I'm going to, notice I have put columns on each one of these sides here. I'm going to take the value for each one of these subjects, and I'm going to get the difference between this value and also the average from this group, and then I'm going to square it. I'm going to repeat that one more time. I'm going to take this value, I'm going to subtract it from the average, and then I'm going to square it. And after all that's done, I've got the differences for each subject from the mean, and what I'm going to do is I'm just going to sum those for each different group. Simple enough. Right there for each group. And already you can tell that there is somewhat of a difference. However, what I'm also going to do, because I'm going to get the sums of the squares for the error or for within groups. And when they talk about within groups, it's talking about within each one of these groups. I am getting this value within each one of these groups. So I'm going to sum that value, and it's right here. So that value is going to go into my denominator. Now we need to get the numerator, the sums of square of the residual, or it's also listed as sums of squares between groups. And the reason why we call it between groups is because now I'm going to look at the actual means and I'm going to compare them between the different groups. And the process is the same. So again, this is the between group sum of squares. And notice it's just the mean of the group minus the grand mean, and then it's squared. And essentially, what we do is we sum all those differences after they're squared into one thing. Now, not to confuse you guys, but in this particular instance, we have to make this sum of squares more comparable to the sum of squares of the error. So I'm going to multiply this value by 7, being that there are 7 individuals or 7 subjects in each group. Hence why our sums of squares for the residual is going to be 50.82. Now we need to discuss what degrees of freedom are. Now, again, this is not a statistical course, but this does come into play with this calculation. Now, the degrees of freedom, if we look at each group, the degrees of freedom is typically the number of individuals in each group minus 1. Essentially, what that means is that out of these 7 groups of people, 6 of these values are allowed to have any value, whatever they want. They can vary, right, as degrees of freedom, except for one. One of them has to be an absolute value. So, if we take all the degrees of freedom for each different group, it's 7 minus 1, which would be 6. Or we could say 35 minus 5, and it's 30. So that is our degrees of freedom within the groups, or the degrees of freedom for the sums of squares for the error. Now we're going to do the same thing for the between group differences. Again, all these values it's going to be the number of groups minus 1, indicating that 4 of these values all have the freedom to have any value they want, or as the name implies, degrees of freedom, except for 1. And that gives us 4 there. And by dividing each one of those values, we get what we call the mean square of the residual, as well as the mean square of the error. And let's just plug in those values and see what we get. So the first one is the mean square, or I'm sorry, the sum square of the residual divided by 4. 4 degrees of freedom. This value should be 47. Let me fix that. It's actually 47.37. Disregard that other value. But if we do these calculations, we get the mean square of the residual, which is 12.71. 47.37 is 30, and we get 1.58. And if we calculate that out, we get an F ratio of 8.02. Now you might be asking yourself, well, why do I need to calculate all that out? Well, you don't have to do those things by hand. The computer will do everything for you. I showed that to you just so you get an idea of how we get the ratio, right? It's the ratio between the mean square of the residual divided by the mean square of the error. And as such, if I ran this through a computer, as what I just did here, I get a summary of all those values. And as you notice, the summary is the same summary as what I did in the calculation. And if we look at our ANOVA table, we have the between groups and also the within groups. And notice that those values are our values. Here are our degrees of freedom between the two groups. And then we also have the mean square between the mean square of the residual as well as the mean square of the error. Now this is where statistically we find out whether or not there is a statistical difference between the groups. So we get an F ratio of 8.02, and we get a p-value of 0.001. That's less than 0.005, indicating yes, there is a statistical difference. But where is that difference? Okay, here's something everybody needs to know. In ANOVA, it just tells us if there is a difference between the group. Now I'm going to back up just a little bit. Back to this formula. Let's say, for instance, there was no difference between the group. That would indicate that this mean square residual and this mean square of the error, that would equal about 1. They would be comparable to 1. So let's just say that they were not statistically different. This would be 1, and this would also be 1. But the higher that ratio becomes, indicates a probability of them being different. But yet again, we don't know where that difference is. So whenever we have a statistical difference when we run an ANOVA, we have to do a follow-up test. We have to do what we call a post hoc test. And with a post hoc test, it's actually going to compare the differences between each one of these groups individually. So it's going to compare machines to barbell, machines to dumbbell, machines to kettlebell, machines to control, barbell to dumbbell, and so forth. So whenever you look in the statistical analysis, sometimes you'll see something called a post hoc test. In this case, a post hoc test was used to determine differences. Post hoc means after the fact. That's all that means. So now it kind of maybe can help clarify some of the confusion if you didn't know what that was in the past. You do not need to run a post hoc test if there is no significant difference. I'll say that again. You do not need to run a post hoc test if there is no significant difference, meaning that my F ratio is closer to 1, that there's no differences between the group. There's no need to see any differences because we know there's not. But if there is a significant difference, where is that difference? And the post hoc test is going to help us determine that. So going back to our groups, we can already tell visually, right, that there is some difference. And it's always good to graph out your groups so you get a better understanding of where those differences lie. Now, before I go into the actual post hoc test, I do need to briefly discuss what we consider error. And I haven't discussed that yet. But there's always a level of error in any statistical test. And I'm sure some of you guys have heard of type 1, and some of you guys have also heard of type 2, which I won't necessarily get into just yet. But you need to know that the more times I run a test on the same subjects, I basically inflate my error. And that's what we call a family-wise error. Family-wise being a group of sets. For instance, I'll just read this definition out. A family-wise error is an inflation of the error when making a series or family of comparisons on the same set of subjects. So, to give you guys a thought, if I'm going to run a t-test between each different group, why wouldn't I have just done that versus running an ANOVA? Well, like I said, ANOVAs actually help correct for this error. But the post hoc tests that are associated with ANOVA are actually sometimes ran automatically if you have the right software, and it does it for you. But let me give you guys an example with our data where I correct for this family-wise error. And the post hoc test will do that, and there are many different post hoc tests that can be done. But some of the two most common in our field is what we call Chefs. Now, Chefs allow for what we call pairwise comparisons, meaning I'm going to check one mean to another mean, plus comparisons of a group mean against a combination of group means. And it's a little bit more conservative, meaning that you're more likely not to get a significant difference between groups. Tukey allows for just pairwise comparison, meaning I'm going to just compare means against one another. And that's the one that we're going to use today. So let's just recap our data. Remember, this F ratio gives us a probability value here, but we don't know where that difference is. So therefore, I need to run a t-test off of all our comparisons. And I've done so right here. Machine versus barbell, machine dumbbell, and so on. And notice when I just do those individual t-tests, I get a number of statistically different values. So machine versus barbell, there's a difference there. There's a statistical difference there. Barbell versus dumbbell, there's also a statistical difference, and all the way down the line. However, now I need to correct for family-wise error. Now, if you guys can remember, our p-values, or in another way to say this, is a set level by which we determine significance. And not to get too confusing, that's what we call our alpha level. Now, our p-value is typically set at 0.05. Now, I'm running 10 tests 1, 2, 3, 4, all the way down the line to 10. That means I need to correct this alpha level to something different. So if I divide 0.05 by 10, the correction now is 0.005, meaning in which if these values are not equal to or less than this correction factor, they are not statistically significant. So if you can recall, these were our original values that were statistically significant. Now, based off our correction, though, there are only 3 groups or 3 differences by which were statistically significant. So, to recap, the ANOVA showed that there is a statistical difference between groups. The post hoc test helps us to helps us to find where those differences are. And the post hoc test also helps to dilute or correct the number of comparisons or family-wise error, so we get an actual true significance. So in this particular case, barbell was statistically different than machines, than dumbbell, and the control. However, it was not statistically different from the kettlebell. So kettlebell and barbell gave us similar results. However, barbell was statistically significant than machines, dumbbell, and also the control. Okay. Now, that was an example of what we consider a one-way ANOVA. We only had one group. There are things such as an ANOVA with repeated measures, kind of what our example showed. However, going forward, I am not going to test you on this particular data. ANOVA with repeated measures are basically the same thing as ANOVA, except now I can test those variables on different time points. The reason why I'm not going to go into too much depth on this is because Excel is not equipped to handle much of these higher level statistical procedures. They can, however, they don't allow us to run post hoc tests. You have to actually do those individually, which become problematic. And because we're just using Excel, I won't complicate this class by using additional software. Know that for you guys going into grad school, sometimes you'll have to use multiple softwares to run different parts of the same test, which gets a little kind of painstaking. So let me give you guys an example. And actually, you're looking at data from my dissertation. This is my actual work. So to give you guys an example, a statistical analysis of all performance variables was executed using a mixed method analysis of variance. That's another way of saying a factorial ANOVA with repeated measures. A 2-key post hoc test was used for pairwise comparisons for each variable and time point, meaning I'm going to look at the differences between each of my variables and as well as those variables at different time points. That's just an example of what it would look like if somebody was going to report it on a statistical write-up. Oh, I'm sorry, in a scientific write-up. Here's how it should be reported by APA standards. A mixed method repeated measures ANOVA showed a statistically significant difference in testosterone compared to p-values. Here I have my F ratio with my degrees of freedom between the groups, degrees of freedom within the groups, my F value, and my p-value. A 2-key post-hoc test shows that the 3-hour and the 12-hour testosterone were significantly different from p-values. And again, that just shows how you would report it. But another way as you would report it can also be visually. And sometimes these are much more useful, especially for individuals who don't have an understanding of statistics. And we're going to get into the visual representation on the next portion. Essentially, if any of you guys become researchers, the idea is to make the literature useful for practitioners in everyday practice. And here you can see that the visual representation is, you can see that there's a difference. Just to give you guys an example of what this is, you're looking at the differences between testosterone. You're looking at testosterone between two different groups. One group getting branched-chain amino acids, one group getting a non-supplement. And what happened is testosterone over time, like after their workout, actually declines in both groups. But the testosterone group actually maintained higher levels than the non-supplement group. So that's just an example of repeated measures. Now that concludes this particular lecture. There will be a video that everybody will need to go through for the practical side where we do this stuff in Excel. Thank you.